Hello, welcome to this session. What we will be doing in this session will be to unpack the paper, the mathematics paper that was set in the final round of the South African Mathematics Olympiad senior paper in the year 2024. As a background, the South African Mathematics Foundation administers several mathematics competitions. One of them is the Mathematics Olympiad, Junior and Senior, and there are 3 rounds. So the first round, the senior, on average between 40 and 45,000 students participate. And by the time they get to the third round, they only 100, just about 100 students qualify into the final round. So you can imagine that these papers, the round 3 senior papers, can be quite demanding. So with those few remarks, we can go straight into the paper in question. Okay, so let's go straight to the very first question. The first question says, a cube of side length n is made up of n cubed smaller unit cubes. Some of the 6 faces of the large cube are fully painted. Some of them, we are not told how many, maybe 1, 2, or 3, or the whole lot. But when the large cube is taken apart, 245 smaller cubes do not have any paint on them. So the unpainted cubes number 245. Right, we were not given n, so the question is, determine the value of n and how many faces of the large cube were painted. All right, so let's first go into a new page. Okay, and let me draw a cube. So I'll draw a cube. The cube has got side n. All right, so these lengths of the sides are all n, and they are broken up into n cubed smaller cubes, and some of them are painted. Okay, so let's just assume at the start that the face that we are looking at, that's the only one that is painted. All right, so let's isolate okay, so this side is painted, and there's the number of squares here. There's only one side. Only these squares that I showed, the cubes, are affected. So how many are unaffected? How many are unpainted? We have that the number of unpainted squares in this case is total number n cubed. You have to take away the number of squares here is n squared. Okay, and if you had 2 faces painted, for example, if you painted the front face and the back face, then in this case here, if 2 faces are painted, Then you have n cubed minus n squared plus n squared. So there are two n squared faces which are painted. If you remove them, you'll get the number of unpainted squares. And like that, now you can take various cases, paint three faces. And the two faces could be these two, the ones which are adjacent to each other. So I could have had only those two faces painted, or could have had three faces painted. I could have had those faces painted. And there you can count the total number of unpainted faces, even in that case. Now, the useful thing in this is that you know how many faces are unpainted. And it was given that there were 245. And you see that the number of unpainted squares can be factorized. And usually there's a square term and another term. So let's try to, if you divide this by 5, you get 5 times 49. So this is 5 times 7 squared. And that gives you the answer straight away. So it means that we are looking at the situation here. Because 5 is 2 less than 7. So you can see n is equal to 7. That's the number of faces. No, that's the side of the cube. And the number of faces, which were painted faces. The question asks for these two things. What's the side? What's the value for n? And how many faces are painted? It has to be 2. We saw there are two opposite faces. All right. So let's get on to the next problem. Okay, you see here that I always write down the solution in advance. In case you didn't understand some of the things I said, you can always freeze in on the written, the prepared answer, and you can get a better version of it. Okay, question 2 says, determine which of the following is the larger. You got two numbers here, square root of 2 plus cube root of 5, and cube root of 5 plus square root of 2. All right. Now, how do you find which is the larger here? You're not allowed to use the calculator. And you got square roots and cube roots of numbers which don't have, they're not perfect squares or perfect cubes for that matter. So you have to figure out something. They don't ask you for what the values are. They ask you which is larger, right? Which is that maybe you might be able to work that out. So let's look at, I've got a new page. Give names to these things. Let A be equal to the let A be equal to square root of two plus cube root of 5. I think that is the one number, and B equal to the cube root of 5 plus square root of 2. When you have these cumbersome numbers, it's always a good idea to give them names. It's much easier to work with symbols than to work with you know, awkward numbers like this. Okay, now we can get rid of the outside square root by, by squaring on both sides. And here you can get rid of the outside cube root, cubing on both sides. Now you've got both numbers have got two different exponents, and to compare them, we should try to get the exponents to be the same. And that can be done. If you cube this, you get a to the sixth. And if you square this, you get b to the sixth. So let's do that. A to the sixth is the cube of this, and b to the sixth is a square of this. So that is 25. 5 squared. 2ab is 10 root 2. And square this, you get 2. Okay. Oh, I should have been cubing this thing. Yeah. Now, how do you cube a sum of two numbers? There is a general formula for that. A plus b all cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. So if I'm cubing this, I'll say it's 2 cubed, which is 8, plus 3 times 2 squared, that's 12, times b, that's cube root of 5. And then I get plus 3 times this times the square of that. 3 times 2 is 6. And the square of this, square of cube root of 5, is cube root of 25. You can square inside. Because when you're squaring 5 to the 1/3, it's the same as 5 to the 2/3, and that is the same as 5 squared to the 1/3. See, and that's the cube root of 25 here. So, and then there's still one more term, and that is the cube root of 5 times cubed. That's just 5. And that works out to 13 plus 12 root 5, 12 times cube root of 5, plus 6 times cube root of 25. Okay, now we have to sort of, this is 27 plus 10 root 2. Now, to find out which is bigger, we have to make some estimations. Like for instance, b to the sixth is 27. 10 root 2 is the same as square root of 200. The square root of 10 squared times square root of 2. And square root of 200 it lies between 14 and 15. So it's certainly less than 42. 27 plus 15. And it's bigger than 41 because this one here is bigger than 196 is the square root of, is 14 squared. So this number here is between 41 and 42. Okay. Now let's just have a look at the other one. This other thing is a little bit more complicated. I'm going to create some space here. Okay, let me just take my phone off. So the other number is this one here. So I got b to the 6 is less than 42. Let's have a look at a to the 6. We said it's 13 plus 12 times the cube root of 5. Sorry, it's 12 times the cube root of 5 plus 6 times cube root of 20, cube root of 25. Okay, let me try to see whether I can put the 12 inside. And this 12 cubed, this is the cube root of 12 cubed. 12 cubed is 1,728. So if you do this, you get 8640. 12 cubed times 5, you can calculate it. And here, 6 cubed times this is cube root of 6 cubed is 216. So this is 5,400. Okay, now we can estimate these cube roots because let me just create some space here. I know that b to the 6 lies between 41 and 42. Let me make some estimation here. Well, for one thing, I know the cube root of 8,000. So I can make this thing greater than the cube root of 8,000 is 20. 20 times 20. And we want this to be greater than what? Well, the closest I can get to is 4,096 to 16 cubed. So you can come to 16. 16 cubed is 4,096. It might be easier to take 10 cubed. This is greater than 1,000. And the cube root of 1,000 is 10. I can even take 10. So what do you got? You got 13 plus, this is 49. So this number here is bigger than 49. This is less than 42. So that gives you the answer. If I had taken 10 here, I would have got 33 plus 10 is 43. And still, even that would have said that this number is bigger than 42 and this is less than 42. So the larger will have to be A. This one. Square root is the larger. That was the question, which is bigger? All right, so yes, you have to bring both to the same thing so you can make comparison. And here we took the same number inside the cube root, and also we took the same exponent, which we chose to be as 6. All right, so let's get on to the next one. Let me just show you the answer to this. We'll take this. Okay, so I show you this so that in case you are going over this, you can see the actual, it's about the same numbers that I was using. Okay, so let's get on to the next question. The next question says a lattice point is a point xy in the plane where both x and y are integers. Now, when you take all the points which are integers, they are actually they will be like 1, 1, 1, 2, 1, 3, and so on. And if you look at all these points, they actually they are they lie on lines like this. So these are integers 1, 2, 3, and this way, if you go 1, 2, 3, the y coordinate is also an integer, and therefore the points that we are looking at are the intersection of these points. So these are the lattice points. Those points have got both the coordinates. They say x and y are both integers, and they could be positive or negative. So you can have this entire grid, the whole plane can be regarded as a grid. Okay. Now, then it says a single strike by an L-shaped punch changes the color of the 4 lattice points. Okay, now they give you the lattice points. I'm going to just plot them here, for instance. Let's call this AB. A plus 1B is 1 unit away from here. AB plus 1 is the same x value, but it's 1 up there, AB plus 1. And AB plus 2, that's the last one, is the y coordinate is increased by 1. So this is a single strike by an L. Now you can see the L-shaped punch, some kind of an instrument. It changes the color of these 4 lattice points. So what's happening here is that you got some object which is changing 4 colors simultaneously. But oh yeah, they are colored black or white. All right. So and then you got these L shape. The L shape can go anywhere. This L shape punch can go, but it's always the same shape. So you might hit one of these points as well and change the color. So what happens is it changes the color. If it was white, it goes to black. Right? Because they were originally it's either black or white. And if it's a black, it changes to white. Now, all the lattice points are initially colored white. Prove that after any number of strikes of the punch at any lattice points, the number of black lattice points will be either 0 or greater than or equal to 4. Okay, now this is going to be quite a demanding problem, and I hope I can explain it. So what's happening here is that, okay, suppose instead of white, I'm going to call it red. So in the beginning, all these points are red, all red. Okay. So what do? You take your punch and you punch 4. And when you punch 4, you see that those 4 red will all become 4 black. I'm calling it rather than white and black because I can't draw a white dot on a white paper. You can't see it. So we'll call it red and black. So the punch actually, it does something to 4 points. So in the beginning, this is what I will have this because there was nothing there, and took my punch somewhere, and I got this, and the rest are all red. Remember, the rest of these are all red. Okay, so this is step 1. Right? Step 2. Step 2. I'm going to punch this scenario all red here, and my L could be the various positions. You could have L hitting that one, or you could have had L. No, recording. You can call Baba. Sorry about this. All right, so you've got now the second one. You can hit 1 black, 2 blacks, 3 blacks, or 4 blacks, and those colors will change. So what happens? Excuse me. Is that excuse me for just a moment. So if you had, you could have had, for instance, you could have a configuration which is the next round. Uh, it could be hitting just this 1 black, in which case I will have these still remain the same, and you'll have this one changes to white. Or you could hit 2 blacks, in which case these 2, like those 2, will change to red, while the other 2 remain as they are. Or you could have had oh yes, I should have said when this black is hit, then the L shape is going to there are red elsewhere, and those red ones will all become black. So this is where the L shape, your punch hits only that one. Now, for the punch to hit this one here, it will hit this, that which is red, that becomes black, and like that. See? So now you can see the number of black in this case is 4. In this case, it's 6, right? And in this case, it's 4. See? Now, if you had, now your L shape, it can't hit exactly 3 in this case, because that means it will be sitting over this whole thing here. So it can only hit 4 at a time. If your L was the second round, if it went exactly on that, then you will have all the blacks would disappear and you'll have only reds. In which case you got no black. See, so what happens is you can argue this thing out by saying that if you had 4 black at any given stage, so okay, so suppose at any given stage you've got n black. Right. And now you take your punch and you cover 4 of those squares. Some of them you might cover, some of the blacks you might cover none, and so on. But you take your punch and you hit it. So if you covered 4 blacks, then you will have those become 4 reds. So what happens is that the number of blacks is reduced by 4. Right? If you have 3 blacks, then when you cover this thing up, those 3 blacks becomes red. So the number is reduced by 3. 2 blacks, the number is reduced by 2. 1 black, the number is reduced by 1, and so on. Right? But what happens is when the 3 blacks is reduced by 3, the other one would have been a red, and that becomes black. So the number of blacks now become -3 plus 1. Here too, the punch, it only changes 2 blacks and they become red, but the rest of the punch will be hitting the reds, so those will change into black. And here the same thing happens. So it means the change your n goes to n minus 4 or n minus 2 or n plus 2. Now, this is not the only way in which your punch can hit this thing. I could have had the original configuration could have been this. The L-shaped could have hit a setup like this, right? And if you take all the possible cases, you'll see sometimes you can actually have the number n actually can increase by 4. Because if I took the L-shaped and hit it in some other part of outside all the dots which are already colored, then I would create 4 new black ones. So the n can become n plus 4. It can increase by 2 also. And then, yeah, it could be n. Right. So the n can be increased by 4, 2, 0, or 1, or 2, or it can decrease by the same amounts. It's quite difficult to explain this thing, but I hope you're getting the gist of what's going on. Okay, so now, since the changes can only be 2 or 4 or 0, that means you can, and as you saw, -3 plus 1, -2 plus 2, and so on. They're all, the changes are an even number, and you're starting with 4. So if you increase 4 by an even number or decrease it, you'll get to another even number. And each time you are increasing or decreasing by even numbers. So the number of blacks is always even. That's an important observation. It's always even, right? Now the question is, show that the number of blacks is either 0 or 4. Right? That's what the question is. In other words, show that 2 is not achievable. Show that 2 is not achievable. Because you want the number of blacks to be either 4, 0, or greater than 4, greater or equal to 4. Right? Now, for 2 to be achievable, you need to have that one of these equations. One of these equations must be equal to 2. You can try it out and you can see that there are only 3 cases. You'll have 4 minus 2 equals 2, or you will have 6 minus 4 equals 2, or 0 plus 2 equals 2. These are the only ways in which you can get exactly 2 from these. Right. In this case here, your original one was 4, and yeah, you can never get exactly 2. You can try out different configurations, exactly 2 blacks. See, because originally your original configuration would, if it's 4, it could be any one of these, that one, or that, and so on. And you can place your punch on these, and you will never come to 2, see, on any one of these. And here, this is a little bit trickier one. It means the one just before this, you would have had, to get to 6, you would have had to add 2 plus 4. So you got 4 new blacks created somewhere, and then you got two isolated ones, right? And in this case here, this 4 new blacks would have been created from 4 whites, right? The previous case. So you come back to the situation where you have exactly 2. And that's not possible. And this last one is not possible, if you think about it, is because you can't have a L-shaped covering exactly three dots. That's not possible. Because the L shape, whenever it covers 3 dots, it must cover that one as well. All right. So it takes a while to show that 2 is not achievable, and therefore the number of points is either 0 or at least 4. Okay, so this is, as I said, now it's very tricky to explain it, but hopefully you'll be able to make some sense of this whole argument here. Okay, so you can have a look at this and try to understand how the conclusion is reached. Okay, so let's get on to the next question. This question says that find all functions f from integers to integers such that, okay, so you are creating integers from integers. And the rule, there's a single function, f, which has this rule. So you need to find what the rule is. Okay, now, like for instance, if I just take a guess, take a random function, say, for example, if f of x equals, say, 2x, right? Then f of m plus n is 2 into m plus n plus f of m minus n. I have to substitute m minus n for x, and minus 2fm. F of m is 2m, and that is equal to 2m. Yeah, exactly 2m. Because 2n and minus 2n cancels off. Right. So, but now we want to land at 6mn squared, not 2n. Okay. So we have to find out what is this function. Right? It's obviously not this now because we just proved it's not that. But how do you find this function? All right. So the way to do this is just to look at. Let me go to I'll use this one for the time being. Now I can take any integers now, any integers to substitute here. But I notice this becomes 0 if either m or n is 0. So let me make it, say, n equals 0. If n equals 0, I got f of m plus f of m, which is 2fm, minus 2fm. So I get 0 on the left-hand side, 0 on the right-hand side. That doesn't help. Let's try m equals 0. Then you got f of n plus f of m equals 0 minus n minus 2f m is 0, m is 0 on the side. So you'll end up with that f of n plus f of minus n equals twice f of 0. And this is interesting because it doesn't matter what your n is. F of 500 plus f of minus 500 is the same answer. It's twice whatever f of 0 is. So let's give a name to f of 0. We'll call it p. So just remember f of 0 is p. And f of n plus f of minus n is 2p. Okay, I want to get onto a new page, which means I'll have to clear out all these drawings. And we had this f of n plus f of minus n equals 2p. And we also had that master formula, f of m plus n plus f of m minus n minus 2f of m equals 6mn squared. I think it's that. Is it m squared n or mn squared? It's one of the two. Mn squared. Yeah, okay. So I got it right there. All right. Now, at this stage here, now we have to sort of start speculating what this function will look like. You see, this is quite a familiar object, mn squared, when you are cubing m plus n. We saw earlier on, we had a term like a squared b and ab squared also. So when you're cubing this, and if you're cubing m minus n also, you have this term featuring here. So that gives you an idea as to what your f would possibly look like. It looks like a cubic function. See, if you substitute m plus n into a cubic, you'll end up with terms like this. So we speculate that f is a cubic polynomial, to be precise. So let us say, suppose f is a cubic polynomial, but there are any number of cubic polynomials. So oh, by the way, p is f of 0. And the general equation for a cubic polynomial is, so let f of n, remember your input are all integers, is equal to a plus bn plus cn squared plus dn cubed. And we need to calculate a, b, c, and d. Okay. Notice that f of 0 is a. So a is actually p here. So we said f of 0 is. So we already know the value for a, it's p. Okay. We also have that f of n plus f of minus n is 2p. So let's just put this thing down, 2p. And this is f of n. It's p plus bn plus cn squared plus dn cubed. This is your f of n. And f of minus n, you have to replace n by minus n. You'll have p minus bn. You replace n by minus n, you'll have beta minus n. And if you replace n by minus n here, it doesn't change. Minus n all squared is still n squared. But here it changes. So if you replace, so now this is your f of n. This is f of minus n. And when you add these two, you're going to get 2p. Well, you'll see here that p plus p is cancels. Bn minus bn cancels. Dn cubed cancels. Or p plus p will cancel with this 2p. So you have 0, and you'll have 2cn squared. These are the only survivors. And therefore, and this is no matter what your n is. So you can make n equal to 1, for instance. Then you get c equals 0. Okay, so now we've 2 down. A is f0 and c is 0. So your actual function is C is 0. So I can take it out. So I still need to calculate B and D. So I'll need a lot of space. Because I'm going to substitute these values, m plus n, m minus n, and m. And I know that's going to be equal to 6mn squared. And I'm going to use that to calculate, to see whether I can get one of the other coefficients. Okay, let me just put the 6mn squared on one side. And that is equal to f of m plus n plus f of m minus n minus 2f of m. Now, f of m plus n is p. Now, b, the n now is replaced by m plus n. I got a cube here, so this is d m plus n all cubed. Now, this part here is f of m plus n. I'm going to add to that f of m minus n. So it will be p plus b into m minus n plus d into m minus n all cubed, because I'm replacing your n by m minus n in this equation. I've got minus 2 fm, so it's minus 2. Fm is a plus, no, I'm sorry, p plus bm plus dm cubed. Now this is quite a long thing here. Now let me try to simplify this. Oh, take all these things out. Okay, I got 6mn squared. Okay, I'm going to do some fast work here. P plus p minus 2p is 0 there. Right? So let me just get rid of that. And here, what's left here? You got bm plus bn. And here you have d. M plus n all cubed. M cubed plus 3d m squared n plus 3d mn squared. Right, that's just this part here. I'm going to add to that, the p's cancel. We add to that bm minus bn. Right, that's finished. Plus, I got all these. It's d m cubed. Now we got m minus n. These signs alternate. You have minus 3d m squared n. Oh, there was a cube term as well. Plus d n cubed. See, dn cubed, the last term. Here you have plus the dm n squared minus dn cubed. See, if you replace the n by minus n here, this is what you get. Right. Now we're adding all this stuff. So you got bm. Oh, you still have this last term. You got minus 2bm minus 2dm cubed. So you just have to keep going doggedly. So you got bm plus bm is 2bm. 2bm goes away with that. All right. So you got bn minus bn. Okay, that goes away. dm cubed plus dm cubed is 2dm cubed. And that goes away with that. You also have dn cubed minus dn cubed. That goes away. And here also you got 3dm squared n minus this. Everything goes away. The only thing that survives is this one here. And that is 6d mn squared. Ah, now you can see. From here you can see immediately that d must be 1. Well, the left-hand side is 6m squared. So d is equal to 1. So although we had a horrible thing, so many hundreds of terms here, you finally can get the value for d. So in other words, your polynomial is going to look like this. Your function f of n is equal to p plus bn, and the c term was 0, and here you have n cubed. Now, interestingly, right, this is the answer. That means your function is always looking like this, where p and b are random. P and b are any two integers. So there are lots of solutions for this. So p and b are any two integers. If you try substituting m plus n and m minus n and all that, and try to work the left-hand side out, you will land up, I tried it, it land up with 6mn squared, exactly. Well, anyway, it's almost the same as this calculation. So that's where you are. All right, so this is your answer to this question. And p and b are any two, like for instance, fn can be 3 plus 5n plus n cubed. That will satisfy that equation that we had.